So now is the time to move away from structural mechanics problems and get into solid mechanics and solving solid mechanics problems in linear elasticity, small strain linear elasticity with the finite element technique. So right now what I'm going to do is recapitulate the essential parts of linear elasticity theory that we will use in this course. And you better be this will be a short recapitulation, quick recapitulation, and if there are missing links, things that you don't understand, please look up basic theory of elasticity textbook. So we start from the assumption that we have a three-dimensional body occupying a volume V and surrounded by a surface which we will call delta V. On the body, at each and every point on the body, the body is described, say, in some coordinate system, and a point on the body is denoted by x at a time t. So at each and every point on the body, we have a body force field specified, which can vary with x and t. And on certain parts of the surface of the body, we have a traction field, a surface traction field, which we'll call t bar, specified as well, so that the total force on the body, total external force on the body is given by rho b dv integrated over the whole volume plus t bar ds integrated over the whole surface, where a small element on the surface is ds, and this is for body force per unit mass. So you have to multiply it by mass by rho to get the total body force. So this body force that we are taking is per unit mass. Sometimes we define the body force as per unit volume, in which case this rho will not appear. Now, if you take any surface on, if you cut this along any surface and and draw the free body diagram of this surface, let's say, has an outward normal n, then the traction on at this point where the outward normal is n is related to the stress right next to the surface by what is known as the Cauchy relation, which is T equal to sigma times n. The equilibrium equation follows from the equation of motion, follows from the conservation of linear momentum, and it is written in tensor notation. It is written as sigma ij comma j plus rho bi equal to rho ui double dot, the double dot indicating second derivative with respect to time. I hope you understand the meanings of this. Sigma ij comma j is also written, can also be written like this. And if you want to write this in vector notation, then you write so this is the divergence of the second order tensor sigma. Now, in most cases that we will encounter in this course, we will deal with quasi-static situations where we assume that this acceleration term is very, very small compared to say the body force term, and therefore we will take it to be zero and analyze situations where this is the governing equation of motion. There is a qualitative difference in terms of the equation describing a fully dynamic situation where this term is not small, and this equation which is for quasi-static situations. So the nature of the differential equations are different, and therefore the solution techniques for the full equation with the right hand side and the solution technique for the equation without the right hand side are significantly different. Right now we will concentrate only on this case. If time permits, we will look at how this term is handled. I'm not sure whether that will be possible, but this is the equation that should interest us at the moment. Now, on the portion of the body where T bar, the specified tractions are applied, that portion of the body is called delta Vt. So it's a part of delta V. And on that portion, following the Cauchy rule, we must have the applied traction equal to sigma ij nj, which is a kind of a boundary condition, is a boundary condition, not kind of a, it is a boundary condition that the stresses have to satisfy on the parts where T bar is specified. Also, the law of conservation of angular momentum dictates that the stress tensor is symmetric. So this is always the case because of the law of conservation of angular momentum. There are situations when this does not hold, but those situations are rather special and should not concern us here. Now, uh, these are equations in stress, and this is the boundary condition in terms of stress. Stress right next to the boundary has to be Ti bar has to be equal to the stress right next to the boundary. So the equations of motion give you three equations. Remember, I is the free index. So there are three equations of motion in terms of the nine components of stress, sigma ij, out of which six components only are independent because of this relation, because of the symmetry of the stress tensor. So this is all about the six components of stress which are connected through the equilibrium, three equilibrium equations. Now there are three components of displacement and also nine components of the small strain tensor. So the small strain tensor is defined as epsilon ij, which is and we use this small strain tensor which has half ui comma j plus uj comma I. The meanings of these are del ui del xj and del j del xi, del uj del xi. So this is the definition of the small strain. It has to be revised when your deformations are large. This assumes that the gradients of deformation, that is these kinds of terms, derivative terms with respect to the spatial variable, are small, and therefore terms containing product of two gradients of displacement are even smaller and they are neglected. That's how we get this small strain tensor. When this is not the case, you have large strain tensors, and that is the story for another day. So this is again a symmetric tensor, just like the stress, which you can easily see by reversing I and j. You get the same expression as ij. So epsilon ij and epsilon ji are the same, which means that again there are six independent components of strain which has to be determined, and these are known as strain displacement. This is known as the strain displacement relationship, which connects the strain, each of the strain components, each of the nine strain components, to derivatives of the displacement components. Now, when you determine, when you have the displacement components and you determine the strain components, it is straightforward. You just take these derivatives and add them together, divide by 2, and you get the strain. However, when you have strain components and want to integrate them to get the displacement, you cannot do it in a straightforward manner. The strain components have to satisfy what is known as the compatibility equation, which is given by this. Now, the compatibility equation assures you that fulfillment of the compatibility equation assures you that the displacements that you get by integrating the strains, starting from the strains, the displacements that you get are single valued and continuous. This compatibility equation, as you can see, there are four free indices, so there are actually 81 compatibility equations. But many of the compatibility equations, in view of the symmetry of the strain tensor, and also the fact that del xi del xj of something is same as del xj del xi of the same function, because the order of differentiation can be reversed. You also have a symmetry with respect to these two indices. Given all these symmetries, many of these 81 equations are actually similar, same as another of those 81 equations. And finally, you have only six of these independent equations in 3D, and you have only one in 2D. Okay, and in 2D, if you have, for example, a state of strain which is given in terms of the position as this and this, you can easily show by using the compatibility equation that involves 1 1 2 2 and 1 2. You can easily show that these three strains will not in general be compatible unless this condition is satisfied. So all strain components will are not compatible in the sense that they will not give you a single valued continuous displacement field when integrated. However, the reverse process, when you have a displacement field, you can just take its derivative, use the strain displacement relation to get the strain. So displacement to strain is straightforward. Strain to displacement requires checking of the compatibility condition. Okay. So, so again, we had three equilibrium equations, and we have now this nine strain displacement relations. We have these nine strain displacement relations for each of the epsilon ij's. So we have 9 plus 3 equations, so 12 equations so far, 6 components of stress, uh, 6 components of stress, 6 components of strain. So uh, we have 6 equations here. We have 6 equations here. So we have six equations here because the symmetry of the strain tensor has to be taken into account. So 6 equations, 6 strain displacement relations, 3 equations of equilibrium gives me 9 equations. I have 6 stresses, 6 strains, and 3 displacements. So I have altogether 15 variables. I am short by 6 equations. So these 6 equations, so far what you have got is the equilibrium equation, or the equation of motion, which is derived, as I said, from the equation of linear momentum. The symmetry of the stress is derived from the equation of angular momentum. These are basic physical laws. Similarly, the strain displacement relation is a geometric relation. It's a description of a geometry of deformation. So this is also, so to say, God-given. So with these God-given equations, we have 9 out of the 15 variables that we have. So now we need some man-made equations which come in the form of what is known as constitutive equation. Now constitutive equations are equations which relate the 6 components of stress with the 6 components of strain. And this can take many forms depending on the material, but we will concentrate in this course on linear elasticity, and we will assume that stress strain laws follow what is known as the generalized Hooke's law, which requires that we know these stiffnesses Cij, which is a fourth order tensor, and these are just numbers that can vary from point to point, that may vary from point to point, but that are not dependent on the strains themselves. So this module, this stiffnesses or moduli do not change with the state of strain. So these are constants. That is your generalized Hooke's law. So from a thermodynamic point of view, uh, we can we can think of a function, a scalar function called the strain energy density function, which is a scalar function of the strains, of all the strain components, such that if you take the derivative of this with respect to epsilon ij, you get sigma ij. So the existence of such a scalar function is uh, is uh, is indicated from thermodynamics. And for a reversible material that we are looking at, so if you release the stresses, the strains go to zero. If you release the strains, the stresses go to zero. So it's a completely reversible material. And for a reversible material, you can show that this kind of an equation actually must exist. So we must have a, strain energy density function u, which has units of energy per unit volume. So U has units of energy per unit volume. And uh, in our case, U is going to be a quadratic function of strain, because when you take its derivative, you will get a linear function of strain, which is already known to you through this linear constitutive equation. Therefore, this is another way of stating the constitutive equation. So in our case, this derivative will simply lead toCijkl. So U is so formed that you have a quadratic function containing theCijkls, derivative of which with respect to epsilon ij will give you sigma ij. So U for a linear elastic material is a quadratic function of strain. However, for other kinds of material, for nonlinear materials, you can have different forms of U. It's not necessary that it has to be always quadratic, but for the sake of this course, we will stay confined to more or less materials that obey a quadratic strain energy density, that have possess a quadratic strain energy density, and therefore they have a linear stress strain relationship. Now this equation can be integrated, so you can integrate sigma with respect to epsilon ij from 0 to some strain epsilon to get the total strain energy density at a point at a strain at a total strain of epsilon. So this is the way you will get the strain energy density at a point, which is same as this. And as I said, this is another way of the stating the generalized Hooke's law. Now, in view of the symmetry of stress, which is sigma ij equal to sigma ji, and the symmetry of the strain, Cijkl will have several symmetries. For example, sigma ij is Cijkl epsilon kl will mean that sigma ji is Cjikl epsilon kl, but sigma ji and sigma ij are same, so it will automatically mean Cijkl and Cjikl are same. Similarly, it will also mean Cijkl will be same as Cijlk. So this is also follows from the symmetry of strain. And in view of the fact that U exists, you will also have uh, del square U del epsilon ij epsilon kl will give you Cij kl, but will give you Cklij. But we know that these two derivatives are same because this is a continuous function of the strains. Therefore,Cijkl must be same as Cklij, which is what this symmetry. So in general,Cijkl has 81 there are 81 constants that define CIJKL, but because of these symmetries, the number of constants come down to 21. So there are 21 independent components of CIJKL that we need to determine. Now, of course, there are 9 stress components, sigma ij, and 9 strain components. Now, one way that is used in finite elements quite extensively is to convert this tensorial stress into a stress vector in what is known as the Voigt notation. So in the Voigt notation, we decide on a mapping between and ij and the elements of the vector. So the mapping that we decide here is 1 1 goes to 1, 2 2 goes to 2, 3 3 goes to 3, 1 2 goes to 4, 2 3 goes to 5, and 3 1 goes to 6. So these are all the stresses that we need. 2 1, 3 2, and 1 3 are just equal to these things. Similarly, the strains would be mapped in the same way. So let's call this A. So then we write the stress as a vector of this form. So this is your sigma 1, this is sigma 2, this is sigma 3, sigma 4, sigma 5, and sigma 6. We will sometimes write it as 1, 2, 3, 4, 5, 6, and sometimes we will specifically write down the components of stress that we are putting in this vector. This ordering is important because if you change the ordering, many other things will have to be changed. So it is also necessary that the ordering of the stress and the ordering of the strain be the same. Then the first strain displacement relationship, first stress strain relationship connects sigma 1 1 to all other components of stress. Remember sigma ij, Cij KL, epsilon KL. So I'll write sigma 1 1 as C11 KL epsilon KL, which will give me C1111 epsilon 11 plus C1122 epsilon 22 plus C1133 epsilon 33 plus C1112 epsilon 12 plus C1121 epsilon 21 plus C23 1123 epsilon 23 plus C1132 epsilon 32, and lastly C1131 epsilon 31 and C1113 epsilon 13. Now what you can immediately see is that epsilon 1 to epsilon 21 are the same. C1112 and C1121 by the symmetry of the stiffness matrix is also the same. So these two together can be written as C1112 2 times epsilon 12. Similarly, this can be written as 2 times C1123 epsilon 23, and this can be written as 2 times C1131 epsilon 31. So now I can write this first equation sigma 1 1 as C, this term is this one, then C1122. Remember the ordering, C1133, then fourth is 1 2, and corresponding to 1 2 we have 2 epsilon I2 here. So the shear strains are doubled when you write them in Voigt notation, because this term C1112 times 2 times epsilon 1 2 actually represents the combined effect of these two terms. Similarly, these two terms are represented by this 2 in front of 2 3, and finally this 2 in front of 3 1. You can write down the equation for sigma 2 2, sigma 3 3, and so on. So this will be your now stiffness matrix, not a second order, not a fourth order tensor anymore. And the 21 independent components that are needed are all represented here. The rest of it is symmetric. This is a 6 cross 6 matrix, so it has 36 components, but out of which only the upper diagonal, upper triangular one is needed. The rest is symmetric. So this is also a symmetric tensor, symmetric matrix. So in the most general case, you will have to determine all these 21 by experiments and supply to the finite element program before the analysis begins. Okay, now the way we will do it is we first have the mapping. So, uh, so suppose I want to find the mapping between sigma 3 and epsilon 1. So from the mapping here, I know 3 is sigma 3 3 and 1 is epsilon 1 1. So these two are connected by C3311. So what I mean is C3311 is the component here, right? So when I write this as sigma 1 to 6, I have to remember this mapping carefully. And if I change the mapping, the form of this matrix will also change. So if I change 1 2 to place number 6, then this fourth row of this will move to the sixth row and the sixth row will move to the fourth row. So we have to be careful that we always use the same mapping when going from the tensorial indices to the Voigt indices. Also, please remember the factor of 2 in front of the strains. This is very, very important, and this comes about because this term actually represents C1112 as well as C1121. Now we sometimes, instead of 1 2 3, use x y z. So 1 2 3 is mapped to x y z, which is easy, and this is what the constitutive equation then becomes, and we write it succinctly as this. Okay, so this is my stiffness. Now for an isotropic material, it can be shown that there are only two independent constants required to determine all the components of C. And Cijkl in tensorial form, as you might already be aware, in isotropic linear elasticity is denoted by this. So the two constants are called Lami's constants, and these two have to be determined, and these are connected to your more familiar Young's modulus and Poisson's ratio through equations that you also must have studied in your linear elasticity course. So for an isotropic material, which we will use most often, this is the form of the Cijkl tensor. And now what we are going to do is we are now going to fill up this 6 cross 6 matrix with the moduli of the isotropic Cijkl tensor, and then you will immediately see that for an isotropic material, C1111, 2222, 3333 are all lambda plus 2 mu. So these are lambda plus 2 mu. C 1212, C2323, C3131 are all mu. So these are all mu. And then you have these cross terms, which is CXXYY, or 1122, which is this, C1133, which is this. These are all lambda, and the matrix, of course, is symmetric. So the 6 cross 6 matrix, in case of an isotropic material, has this form, and this is the form that we are going to use most often. It is, of course, possible using the relations between lambda and E and nu, mu and E and nu, to express this matrix in terms of E and nu. That is, of course, possible, and we will also do that in many cases, but I'll leave that as an exercise for you to do it on your own. It's very, very simple. write it in terms of E and nu. Now, in some cases, we will have to deal with materials that are not isotropic. For example, composite materials are not isotropic, but they can be linear elastic. So, in such cases, we have a few special cases which are less special, let's say, than the isotropic case, but nonetheless are also important. So, imagine that I have a block of material, so a big block of material in the XYZ coordinate system, and the XYZ coordinate system is oriented like this. And for this block of 3D block of material, the XY planes are planes of symmetry, which means that if I orient the XYZ axis in this manner with Z pointing upwards, and if I orient it in this manner with Z pointing downwards and the directions of X and Y unchanged, the material doesn't know. The properties are same for these two orientations, which means that if I take the general 6 cross 6, if I take the stiffness matrix and rotate it, remember it's a fourth order tensor, and I rotate it by rotate it through a rotation where the z-axis is flipped by 180 degree. If I apply this rotation to the uh, general stiffness matrix, uh, the stiffness matrix would remain the same. It wouldn't even know that you have changed the direction of the z-axis. Now, for that to happen, and this is kind of something that is done in your elasticity courses, but we are not going to do it here. But suffices to say that if this is to be true, that the material stiffness is insensitive to flipping of the z-axis by 180 degree, then your stiffness matrix must have this form where these are 0. Okay. Now, when this is the case, again, you have to remember the ordering that we have done. The location of these zeros can be here or here depending on the ordering. And for our ordering, this is the form of the stiffness matrix for a material which is called monoclinic and which has only one plane of symmetry. Now imagine a material which is orthotropic, which means that it not only doesn't know if z-axis is flipped, it also doesn't know if the y-axis is flipped. It also doesn't know if the x-axis is flipped. So for all these three rotations which flip the x, y, and z axis by 180 degree, the 6 cross 6 stiffness transforms to itself. In that case, the material is called orthotropic, and it has not one but three planes of symmetry. And many materials, rocks, for example, composite materials, many of them are indeed orthotropic, naturally orthotropic materials, and composites are synthetic orthotropic materials. And for these materials, the stiffness matrix takes this form, and so C 1 1 1 1 2 2 2 2 and 3 3 3 3 might be different in value, but these quantities will be 0, and there are 9 independent constants that you need to determine. 9 independent constants that you need to determine: 1 2 3 4 5 6 7 8 9. 9 independent constants that need to be determined for this kind of a material. For a monoclinic material where there's one principal one plane of symmetry, you have to determine 13 independent constants. That's still a climb down from the 21 that you need in the most general case. In most general case, where there are no symmetries, you need 21. For a monoclinic, you need 13. For an orthotropic, you need 9. And We have another situation which is called transversely isotropic material, where the situation is like in a fiber reinforced composite. So there are fibers running in this direction. Let's call it the Z direction. And you have a plane here perpendicular to the fibers, and this is the XY plane. On this XY plane, if you rotate on this XY plane, the properties are the same. So any rotation that you make will give you back the same stiffness matrix that you started with. Any rotation on the plane will give you back the same stiffness. Uh, Also, it will not know if you have flipped the z-axis. So this axis system and this axis system will also yield the same stiffness. So for this kind of a material where there's one direction perpendicular to a plane of isotropy, is called a transversely isotropic material, and it requires five independent constants, and this is the structure of the stiffness. Note this shows that C1212 is actually related to C1111, and C1122 is related to C1111 and 1122 for this transversely isotropic material. Again, the ordering is important. In some books, sigma xy is put at the end, and therefore this appears in the 6-6 place rather than in the 4-4 place. But we stick to this kind of numbering. So this has five independent constants. So this two are equal. So this is 1, this is 2, 3, 4, and 5. These are the five independent constants. So you have come down from 21 to 5, and if you have isotropy all around in the xy as well as, so any rotation of the axis, the stiffness matrix does not change. The rotated stiffness matrix is same as what you started with. In that case, the material is isotropic, and for the isotropic case, you just need two constants, which are the Lamy constants that we have seen